Welcome to the video help with physics problems for Physics 1B. In this video we'll be doing homework set 3, part 1. That's everything under the headings, the magnetic field and Ampere's law. For 1221 students this covers questions 1 to 7. For 1231 students this covers questions 1 to 9. Problem 1. In this problem we have an electric field of 1500 volts per meter and a magnetic field of 0.40 teslas acting on an electron moving with a velocity v such that it produces no force, and we're asked to calculate the minimum electron speed v. As there's no force, we need to have the electric force and the magnetic force on the electron in equilibrium. So let's assume that our electric field is aligned in this manner. Electric field lines are drawn going from positive to negative. So if we put an electron into this electric field, it's going to feel a force downwards. That will be the direction of the electric force. So to balance this out, we need to have a magnetic force going upwards. Now the formula for magnetic force is F is equal to QV cross B. So our V, our B and our F are all perpendicular vectors. So let's assume that our magnetic field is going into the page. To have a magnetic force going up the page, we'll need to have the velocity perpendicular to both of these. So it will either have to be going in this direction or in this direction. We can use the right hand rule to work out which one. If it's this top one, then the magnetic force on a positive charge would be down the page. So on a negative charge like this electron, it would be up the page. So this is the correct one. So one possibility for the arrangement is here's the velocity is perpendicular to the electric field. This is the electric field and this is the magnetic field here coming up out of the page. Okay, now we're asked to calculate the magnitude of the velocity, the speed. So for that to be the case, we have Fe is equal to Fb, and so we have QE is equal to QVB. These will cancel out and we end up with V is equal to E on B, which is equal to 1500 over 0.40. Solving that on the calculator, we end up with 3,750 meters per second, which is 3,800 meters per second to two significant figures. So that's the answer to part A. Part B says draw the vectors for E, B and V. That's what we've done here. We've shown that if E is going up the page, then V is going to the right and B coming out of the page is a possible solution. Problem 2. In this problem we have an electron beam. So here's our beam of electrons. It's going from south to north. And the energy of the electrons is equal to 12 kilo electron volts. And we're told that this is orientated in the Earth's magnetic field, which is pointing directly downwards. And we're asked in what direction will this beam of electrons be deflected? Well, the force is equal to QV cross B. And this gives us the direction on the positive particle. Here we have a beam of electrons. So using our right hand rule with the V cross B, a positive particle would feel a force to the left, but a negative particle like these electrons will feel a force to the right. So we've got north up here, this will be east, here's south and here's west. And so they feel a force towards the east. Okay, part B, we're now asked to calculate the acceleration of the electrons. So to do that we can use MA, the total force, is equal to Q V cross B. And these are perpendicular to each other, at least when it first enters the tube. So this is equal to QVB. Okay, so the acceleration is equal to QVB over m. So we know the mass of the electron, the charge on the electron, and we're told that this magnetic field has an intensity of 5.5 times 10 to the minus 5 Teslas. And so what we need to do is work out the velocity. To do that, we can use the energy. This is a half times the mass of the electron times the velocity squared is equal to 12 times 1,000 to get it into electron volts times 1.602 times 10 to the minus 19 to get it into joules. And the mass of the electron is given by 9.109 times 10 to the minus 31 kilograms. So substituting this number in and solving for V, we end up with V is equal to 6.4968 times 10 to the 7 meters per second. Okay, now we can substitute everything in here. Charge 1.602 times 10 to the minus 19. V is 6.4968 times 10 to the 7. B is 5.5 times 10 to the minus 5. And the mass of the electron is here, 9.109 times 10 to the minus 31. So solving this on the calculator, we end up with 6.28 times 10 to the 284 times 10 to the 14 meters per second, which let's give it to two significant figures. That's 6.3 times 10 to the 14 meters per second. And it's an acceleration, so it should have a direction, so it's the same direction as this force, so to the east. Okay, part C says how far will the beam be deflected in moving 20 centimeters through the television tube. So we're now told this distance is 20 centimeters. So we could make the approximation that this acceleration is constant over the motion. That would be an approximation, as the acceleration is always acting perpendicular to the velocity, and the acceleration is actually changing the direction of the velocity as it goes. So this equation is actually showing us that the particles are going to be moving around in a circle, as the acceleration will always be perpendicular to the direction of travel, i.e. the tangent to the circle. So we could make the approximation that the acceleration is constant, but we don't need to. So let's not make that approximation in solving this problem. We know that it's traveling in a circle with the circular motion formula A is equal to V squared on R. We can use this formula because we know A and we know V to get the radius of the circle about which it's traveling. So R is equal to V squared on A. Let's keep all our significant figures. So V is 6.4968 times 10 to the 7 squared over A, which is 6.284 times 10 to the 14. Solving that, we end up with 6.71653 meters is the radius of our circle. Okay, now let's draw our circle. Circles obey the equation x squared plus y squared is equal to r squared. So initially, here's our velocity up here. This is x, this is y, and r is 6.71653. So initially, we've got y is equal to 0 and x is equal to 6.71653. But it has moved up a distance to 0.20 meters because it's moved 20 centimeters in the south-north direction, the y direction, along the tube. So what we need to do now to work out the deflection is work out how far it's travelled in the x direction. So we can use this formula. Okay, so to find the final position, we can use x final squared plus y final squared is equal to r squared. So x final squared is equal to r squared, which is 6.71653 squared, minus y final squared, and the final height is the 0.20 squared. So solving this, we end up with x final is equal to 6.71355. And so the change in x, which is how far it's moved in the east-west direction, is equal to the x final minus x initial, which is the 6.71355 minus 6.71653. Now we're going to end up with a negative answer, but we know it has moved in this direction towards the east, so we can just ignore that negative sign. What we end up with is 2.9778 times 10 to the minus 3, which is equal to 3.0 millimeters to the east, is its displacement as it goes through that tube. Problem 3. In this problem we have a magnetic field which is going into the page. We then have a couple of supports which are holding up a wire. This wire has a mass of 10 grams and a length of 60 centimeters, so 0.60 centimeters. And so it's got a weight force mg acting down on it. And we are asked what magnitude and direction of current do we require to remove the tension in this support. So to remove the tension, this bar would be in equilibrium. We'd have a magnetic force acting upwards and directly balancing the weight force. So we'd have FB is equal to mg. Now the magnetic force is given by L I cross B. Let's start by working out the direction. We need to have the magnetic force going upwards, and we know that the magnetic field is coming out of the page, and so our current must be flowing from right to left in order to produce an upwards magnetic force. So current flows right to left. The current and the magnetic field are perpendicular to each other, so we have a sine 90 here. So what we now have is mg is equal to LIB, and we can substitute in to get I, which is mg over LB. So m is 10 grams, so that's 10 times 10 to the minus 3 kilograms. G is 9.8. The length we're told over here, let's make it a capital L, is 0.60. And our magnetic field has a strength of 0.40 teslas. So B is equal to 0.40 teslas. So now solving this on the calculator, we end up with 0.41 amps. And we've got the direction up here, right to left. Okay, so that's the answer to that problem. Problem 4, which is a 1, 2, 3, 1 only problem. In this problem, we have a magnetic field going from left to right like this. The magnetic field strength is equal to 0.50 teslas. Now we have a loop of wire which is hinged about an axis here. Here's our loop of wire with the current flowing through it. This forms an angle of 30 degrees with the magnetic field, and this is the hinge about which it's axised. The size of the current is 0.10 amps. The length of this side is 0.10 meters, 10 centimeters, and the length of this side is 0.050 meters, 5 centimeters. And we're asked to find the torque in this case. And we're told that there's 20 loops of wire, so n is equal to 20. Well, to do this, let's consider each of the sides. We've got side 1, 2, 3, and 4. First of all, the torque inside 1 is given by r cross f, where r is the distance from the pivot point. But this is where our hinge is. So the distance from the pivot point along this side is always 0. So the torque is 0 as r equals 0 all along the side. Now for sides 2 and 4, we'll need to use that the force is equal to NLI cross B. But the currents are travelling in opposite direction for these two sides. So the force will have opposite direction for sides 2 and 4. But apart from that, it will have the same magnitude. And so the torque, because F has the opposite sign, the torque will also have the opposite sign. And so the torque will, from sides 2 and 4, will cancel each other out. So that's nice. That leaves just side 3 to consider. Okay, so for side 3, let's calculate the force due to side 3. This will be given by NLI cross B. To make it a bit easier, let's draw a new diagram where we're now looking from on top. So we're looking down like this at what we see. So we see the current going down into the page. And here's our magnetic field. So you can see our magnetic field will be perpendicular to the current. And so using the right hand rule, force is going to be directed in this direction in this diagram. So let's just calculate the size of that force. That will be N is 20. The length of the side is 10 centimeters. The current is 0.10 amps and the magnetic field is 0.50 teslas. And the magnetic field and the current are at right angles to each other. So we've got sine 90, which is just 1. So solving this, we get 0.1 newtons. And the direction is shown on this diagram. Down there. Okay, so now the torque is equal to R cross F. So R is the vector drawn from the pivot point to where the force is applied. So that is our R vector and this is our F vector. That in there is the 30 degrees. So this here is 60 degrees. There's an angle of 60 degrees between them. Okay, so solving for this. R, the distance from the pivot point is the 5 centimeters, so 0.050. The F we've solved up here, it's 0.10. Now, this is a cross product and they're not perpendicular to each other. So we have sine of the angle between these two, which is the sine 60. Okay, so solving this on the calculator, we end up with 4.3 times 10 to the minus 3 Newton meters. And now the direction, using the right hand rule on the R and the F, you can see the direction will end up parallel to this I. So this will be parallel to the hinge and down the page. So that's the answer to this one. Problem 4 for 1221 or 5 for 1231. In this problem we're given current flowing along a loop of wire like this. The current has magnitude I and we're asked to use Ampere's law to qualitatively describe the 3 paths shown in the figure. So our 3 paths are, we've got path 1, we've got path 2, and we've got path 3. Now what Ampere's law states is that the path integral of B dot ds, So the dot product of the magnetic field and the increments of length along the path are equal to mu naught times the enclosed current. So let's look at what this is telling us about path 1. We know that the magnetic field is coming up out of the page, up the top of the loop, and down into the page down the bottom, and it forms circular loops like this around the wire. So for path 1, to have B dot ds positive, we need B and RDS, so our loop, in the same direction. So our loop and our B are going to go around the wire like this. And in that case, we know that B is constant around that loop, so we can pull it out of the integral. So we've got B ds is equal to mu naught I enclosed. Now what this is saying is add up the little increments of ds all around the loop. So ds, this whole integral here, just turns out to be the length of this loop. So we've got B is equal to mu naught over I enclosed, length of loop. So if it's a circle, that's mu naught I enclosed over 2 pi r, and the I enclosed in this case is just this little I. So what we can say about path 1 from Ampere's law is that the magnetic field is given by this expression, and it's coming up out of the page here and going down into the page here. For path 2, the enclosed current is given by 0, as the current down here is flowing in this direction and up here is flowing in this direction, so opposite directions, and I, obviously it's the one piece of wire, so the magnitude of the current is not changing. So we've got B dot ds is equal to 0 for path 2. Which isn't telling us that the magnetic field's 0 everywhere on that path. What it's telling us is that the average magnetic field around that path is 0. So magnetic field will switch directions somewhere, it'll be positive somewhere, it'll be negative, and those all cancel each other out. For path 3, we can see that the current's flowing in the opposite direction to path 1. So we're going to have the magnetic field going in the opposite direction as well. It'll be going down into the page on top and coming up out of the page below. So same as path 1, but B is in the opposite direction as I is in the opposite direction. This is problem 5 for 1221 or 6 for 1231. In this problem we have a wire with a current flowing through it, I, like this, and we're given a few points. We've got point A, we've got point B, and we've got point C. And the question simply asks us, what is the direction of the magnetic field at points A, B, and C? So one way to do this is to use the Biot-Savart law, which tells us that dB is equal to mu naught over 4 pi I ds cross the direction of r over r squared. Okay, so all we care about is the direction. So in this formula, all we care about is the direction. So the direction, dB, is equal to ds cross r. This is the direction. And so at A, r is drawn in the direction from the wire to the point we're interested in. So that's our direction of r at A, and ds is the direction of the current flow. So that's in this direction here. So just using the right hand rule, you can see at A, direction is up, out of the page. Now at B, in this case r is in this direction and ds is in the same direction. So ds cross B, just using the right hand rule, is down into the page. And at C, here's R direction, and you can see that this is going to be down into the page as well. And as at C, the R is much bigger than at B, this will have a smaller magnitude. Problem 6 for 1221, which is 7 for 1231. In this problem, we have a long straight wire carrying a current of 50 amps. We have an electron traveling with a velocity of 10 to the 7 meters per second, and it's 5 centimeters from the wire. And we're asked to calculate the force on this electron depending on the direction that the electron's traveling. Okay, the force on the electron is given by QV cross B. So to work out the force on the electron, we'll need to know the magnetic field caused by this wire at this point. So first find B. To do that, we can use Ampere's law. So we'll draw a circular loop, which is coming up out of the page here, going down into the page here, and it's got the radius 5 centimeters, like that. Okay, so then we have B dot ds is equal to mu naught I enclosed, and so B is constant around this path, so we can pull it out the front. The integral around the path of ds just gives us the circumference of that circle, which is the 2 pi r, and so we've got mu naught, which is 4 pi times 10 to the minus 7, times the enclosed I, which is the 50 amps, over the 2 pi times the 5 centimeters. So solving this on the calculator, we find that B is equal to 2.0 times 10 to the minus 4 teslas, and it's in the direction we've drawn this path, coming up out the top and going down in like that. Okay, so we've now found the magnetic field here, so now we can solve it for each of these cases. In case A, we're told that the velocity V is towards the wire. So here's the direction of the velocity, and the magnetic field at this point is coming up out of the page. Okay, so V cross B, this will have a force in this direction if it was a positive particle. However, Q is going to be negative, so that's going to switch our direction. So this is F for positive, so the force on the negative particle will be parallel to the current here. You can see that the current's going in this direction, so this force is parallel to the current. So that will be the direction. Let's work out the magnitude. F, V and B are perpendicular, so when we do sine theta, we do sine 90 and we get 1. So the charge is 1.602 times 10 to the minus 19. The negative is going into this direction. The velocity is given by 10 to the 7, and the magnetic field is given by 2.0 times 10 to the minus 4. So solving that on the calculator, we end up with 3.2 times 10 to the minus 16 newtons, and this is parallel to the current in the wire. Now in part B, we've got the same magnetic field as it's set up by this wire, so our magnetic field is coming up out of the wire, but in this case our velocity is directed parallel to the wire. So let's take the velocity as parallel to the current. Here's the velocity. Then V cross B, on a positive charge it would be directed towards our wire. So this is the force on the positive particle, but as this is an electron and it's negative, the force will be directed in the opposite direction, so radially outwards. And so the force, the magnitude is going to be the same, as we've got the same Q, we've got the same V, and we've got the same B, and V and B are still perpendicular, so it will be 3.2 times 10 to the minus 16 newtons, and this will be radially outwards from the wire. And now part C says what happens if it's at right angles to the directions in A and B. Okay, so it's at right angles towards the wire and parallel to the current. So that tells us that it's into or out of the page, which means that V is parallel to B. And as you can see, this is a cross product, and so when these two things are parallel, F is going to be 0. So no force. F is equal to 0. Okay, we're on to problem 8, which is a 1, 2, 3, 1 only problem. So in this problem, we're given two wires. One's got a current flowing out of the page, one's got a current flowing down into the page. The distance between the wires is D, and then a distance R away, we've got point P. And we're asked to work out the magnetic field at the point P. And so this is distance D on 2, and this is distance D on 2. And now what we need to do is work out the magnetic field here. So what we can do is work out the magnetic field from, let's call this one wire 1. And then we can work out the magnetic field from wire 2, and we can just add these together. We need to remember that these are vectors, and so we will need to consider the direction of the magnetic field. Okay, so let's start off just by considering wire 1. We'll need to use Ampere's law, so we'll need to know the distance from the wire to point P. So using Pythagoras' theorem, this is the square root of D on 2 squared plus R squared. And what we'll need to do is draw a path. Let's draw our path going in this direction, so that's the direction of the path. And then we've got, if we integrate around that path, B dot ds is equal to mu naught I enclosed. And so B is equal to mu naught I, which we're told that the current flowing through the wire is given by little I, so mu naught I over, and now we need to divide by the path integral of ds, which is just the circumference of this circle, so that's 2 pi times this here, which is the square root of d over 2 squared plus r squared. And now B is parallel to the circumference increment ds, so B is going up in this direction here. So let's call this angle here theta. Then this is at 90 degrees here because we've got the tangent between the radius of the circle. The angle between the tangent and the radius is 90, so that's 90 there. And so if we draw a triangle this way, this is theta. So we know that sine theta, from this triangle, sine theta is equal to opposite over hypotenuse, so d over 2 root d on 2 squared plus r squared. And from this triangle, we can split our magnetic field B here into a vertical component and a horizontal component, and that's equal to the horizontal component over the total B. So we've worked out our B due to wire 1. And we've drawn the direction there. This is the direction. Now for wire 2, B is going to have exactly the same magnitude because the current in the wire has the same magnitude. The distance from here to here is also d over 2 squared plus r squared. So this will be mu naught I over 2 pi root d on 2 squared plus r squared. Now the only difference is the direction. In this case, here's our circle. B is going to be directed in this direction. And so once again, this is theta. The angle between the radius and the tangent is 90, and so this angle down here is theta as well. Okay, so let's work out the total B. Now, taking into account that these are vectors, you can see that the vertical component's actually going to cancel out because the vertical component will be B cos theta, and cos theta is the same, and the B's have the same magnitude but are in opposite directions for the vertical component. So the total B is just going to be the sum of the horizontal components. So it'll be 2 times BH, which will be 2 times, now the horizontal component is sine theta times B, so sine theta B, and so this is 2 times. Now sine theta is d over 2 square root of d on 2 squared plus r squared, and B is given by this, mu naught I over 2 pi root d on 2 squared plus r squared. Okay, so just solving this, we end up with 2d mu naught I on the top, and down the bottom we'll put this 2 in here and we'll put this 2 in here. So we end up with a pi, and when we multiply 2 square roots we get rid of the square root sign, so we end up with d squared plus 4r squared. And that's what we were asked to show. Now in part B we're asked for the direction, and you can see that the direction from the horizontal components is along this r axis here. So in same direction as r and away from the 2 wires. So it's in that direction. Okay, so that's the answer to that one. Okay, so this is problem 7 for 1221 or problem 9 for 1231. And in this problem we've got a couple of wires. We've got a long straight wire like this. Let's call this one wire 1. And it's got a current, let's call it I1, which is equal to 30 amps flowing through that. And then next to this wire we have a loop of wire like this. That's a rectangle, and it's got a different current flowing through it like this. Let's call this wire 2, and it's got a current I2, which we're told is 20 amps. And we've got a distance here given by A, we've got a distance here given by B, and then we've got a distance L, which is the length of this loop here. Now let's split this loop up into different sides. So let's call this one side 1, we'll call this one side 2, we'll call this one side 3, and we'll call this one side 4. Now what we're asked to do is to calculate the force acting on the loop. So we need to know what's the force. And to do that we're going to need to use F is equal to IL cross B. And so we're going to need to work out, well, what's the force on each of these sides of the loop. Okay, so let's start by considering sides 2 and 4. We can see that at sides 2 and 4 the magnetic fields are perfectly symmetric. So what I mean by that is if we take a little element of length here and an element of length here, because everything's symmetric about here, they're the same distance from this wire, this wire, this wire, and this one are equivalent, then we can see that these are going to have the same magnitude magnetic fields and the same direction magnetic fields, but the current through wire 2 and wire 4 are equal but in opposite directions. So looking at this force equation, if everything's equal but one of these directions is opposite, we can see that the force on this one and the force on this one is going to be equal and opposite. So we can see that the forces on wire 2 and wire 4, if we just summed up each of these little increments, is going to completely cancel each other out because of symmetry. So the net force on 2 and 4 combined is 0 as all components cancel. Okay, so now what we're going to do is we're going to consider the forces on sides 1 and 3. We'll start by just considering the forces due to wire 2. So we're going to now ignore wire 1, and we've got a current going this way with their sides 1, their sides 3. This is a distance B. So we know that the magnetic field on side 1, so that's on this side, due to this wire is given by mu naught I over 2 pi r, but r in this case is B. And then if we use the right hand screw rule, aligning your thumb with the current on side 3, you can see that this magnetic field is going into the page. And similarly, if we work out the magnetic field on 3 due to 1, we've got mu naught I over 2 pi B again, that's on this side due to this one, and again with your right hand rule you can see that this is going to go into the page. So now we've got magnetic fields going into the page like this. If we now consider the force on these two sides, F on 1 due to 3 is given by I, well it's I2 because we've got current 2 flowing through here. L, the length is just little l. These are at right angles to each other, so this cross product is just times sine 90, which is 1, and this is mu naught I over 2 pi B. And then using our rule for cross products, we can see that this force is going to be to the left. So that's just using your right hand rule to get the direction. And F3, again, it's the same current, so I2, it's the same length, mu naught I over 2 pi B. This was into the page, but this I is now down the screen, whereas before for I1 it was up the screen. And so when we use the right hand rule for this one, we get to the right. So what you can see is these two cancel out. So the net force on the loop due to the current in the loop is 0, which isn't really surprising because, I mean, if it wasn't, then when we started running a current through a loop which wasn't in the magnetic field or anything, the loop would start to move, which would be kind of counterintuitive. We wouldn't expect that, and it doesn't happen. So the net force on the loop due to just current in loop is 0. So basically we've shown that all we need to consider is the force on sides 1 and 3 due to this wire 1. So now we can calculate that. So let's call F1 without the circle the force on this side due to wire 1, and that's going to be given by IL cross B, and B in this case is caused by the current in this wire here. So with your right hand rule you can see that's going to be going into the page like this, and we can calculate them with this same formula here, only now the distance between those two is A. So we can write this as, well, this is the I2 is the current that we're considering flowing through here. So we've got I2, this L is L. The cross product, they're at right angles because this is into the page and up the page, so that'll be sine 90, which is 1, and B is given by mu naught. Now this is set up by the current through this wire, so that is the I1 over 2 pi A. And now we've actually been given numbers in the question that we can substitute in for this. So I2 we're told is equal to 20. The length we're told is 30 centimeters, so this is 0.30 meters, so 0.30. Mu naught, that's 4 pi times 10 to the minus 7. I1 is 30 amps, and this is over 2 pi, and A A, we're told, is equal to 1 centimetre. So 0.010 metres. Okay, and now we can solve this on the calculator, and we end up with 3.6 times 10 to the minus 3 newtons, and then we need a direction, and so we can use the right hand rule. L, the direction of L, that's the direction of the current, so that's up the screen, and B is going into the screen, and so when we use our right hand rule with that, we can see that this force is to the left. Okay, now we need to do a similar thing for F3, this side here, and we're working out the force due to this wire here. So that's also going to have a magnetic field going into the page, but it's going to be a smaller magnetic field because we're further from this wire 1. So we'll use IL cross B again. The I is the same current flowing through that loop, so I2. The length of side 3 is L. The cross product, we can see that this is into the screen still, and this current's going down the screen. So those are at right angles, so it's going to be sine 90 or 1. So then we just need to work out the B, which will be mu naught I1, because it's due to wire 1, so it depends on the current through wire 1, over 2 pi, and then it's the distance from this wire, which is A plus B. Now, these are all values that we're given. So we've got 20 times 0.30 times 4 pi times 10 to the minus 7 times I1, which is 30, over 2 pi. And then we're told A is 1 centimetre and B is 8 centimetres. So 1 plus 8 gives us 9 centimetres, so 0.090 metres. And then we can solve this one on the calculator, and we get 4.0 times 10 to the minus 4 newtons. And now we consider the direction. So in this case, I2 is going down the screen, whereas for F1 it was going up the screen. So down the screen and then into the page, and you can see that this force is going to be to the right. Okay, so these two forces are in opposite directions, so they're going to cancel each other out. So the net force is going to be, this one's bigger, so this one's going to win. So it's going to be 3.6 times 10 to the minus 3 minus 4.0 times 10 to the minus 4, and that gives us 3.2 times 10 to the minus 3 in this direction, so to the left. So we've now calculated the force on that wire.